have an example of a function here where we want to find the intervals of increasing and decreasing, and we're going to find some other things as well, local min, max, concavity, inflection points, and then using that information to sketch a graph. But first of all, let's find intervals of increasing and decreasing, and the way we do that is by looking at the derivative. So first of all, I need to find the derivative of f of x, and I'm going to have to use product rule to do that because I have a function times another function. Alright, so product rule says the first times the derivative of the second. Now that's 6 minus x to the 1/2 power. So it's going to be 1/2 6 minus x to the negative 1/2. And then chain rule, I have to take the derivative of what's inside of that, which is a negative 1. So that's my 1 d2 plus 2, which is, I'm going to write this as 6 minus x to the 1/2 power, times the derivative of the first, which is x. Okay, now we got to simplify this to find our critical points. So let's see what we can do here. My first expression is a negative x over 2 times the square root of 6 minus x. Did you see how that worked? I have x times negative 1 in the numerator, so that gives me the negative x. I have the 1/2 means 2 in the denominator. The negative exponent here brings down 6 minus x to the 1/2 power into the denominator, and then that becomes the square root, plus the square root of 6 minus x. Okay, now if I'm going to get these together, I need to get a common denominator. I need to multiply this expression by square root of 6 minus x over the square root of 6 minus x, and actually 2 times that, so I can get my common denominator. And when I do that, I end up with 2 times, well, the square root of 6 minus x squared, which is just 6 minus x, over 2 times square root of 6 minus x. Those 2's want to cancel out, but don't do that because we just multiplied the 2 in to get a common denominator here. And I can bring them together now and have a denominator of 2 times square root of 6 minus x. And the numerator, look what happens. I end up with distributing the 2. I have 12 minus 2x plus another negative x gives me minus 3x. Okay, so now if I'm trying to find my critical points, which are the things that I need in order to determine intervals of increase and decrease, I need to do two things. I need to set the numerator of my derivative equal to 0, and then I also need to set the denominator of my derivative equal to 0, because those two things will give me where the derivative is 0 or undefined, and that's the definition of my critical points. From the first one, I end up with x equals 4. From the second one, I end up with x equals 6. So those are my critical points. Alright, now, using that, how do I find my intervals of increase and decrease? So I'm going to set up a number line, and I'm going to mark on the number line my critical points. And remember, this number line is referring to the derivative, and I'm going to pick test points to just plug into the derivative to see if they're positive or negative at these points. I'm going to pick 0, for example, something less than 4, something between 4 and 6, how about 5, and then something greater than 6, how about 1,000? And I'm plugging it into the derivative. The factored version of my derivative would be the easiest, so this is actually the easiest version to plug in. Again, all I care about is positive or negative. For example, if I plug in 0, I have 12 minus 0, so that's going to be a positive in the numerator, over 2 times square root of 6 minus 0, which is also positive. That means if I plug in anything less than 4 into the derivative, I have a positive value. If I plug in the number 5, what changes? The denominator stays the same, because I have 6 minus 5, that stays the same. The numerator becomes 12 minus 15, so that's going to be negative. So anything between 4 and 6 ends up with a negative value of my derivative. And now watch what happens here. When I plug in 1,000, well, the numerator is negative, but the denominator, I have the square root of a negative. That's not possible. So what happened here? Well, remember that the function domain of f of x, what's under the square root cannot be negative. So this needs to be greater than or equal to 0, which means negative x is greater than or equal to negative 6, which means that x, when I divide both sides by negative, I flip my signs, x has to be less than 6. The domain of this thing is only negative infinity up to 6, 6 included. So here, even though 6 was a critical point, nothing beyond here exists. Okay, so even if you didn't notice that right at the beginning, it's okay. The sign chart will still point you in that direction. So that tells me then, I have my intervals of increasing and decreasing now, because when the derivative is positive, that means I'm going up, and when it's going negative, my function is going down. So we can summarize by saying f of x increases on negative infinity to 4 and decreases on the interval from 4 to 6. Now, how do you know if you should include 4 or include 6? Honestly, It's a preference of the professor. The technical definition of increasing says that as long as your values are greater than or equal to as you move along, you're okay. But we're just going to leave them at open intervals. I think that makes total sense. All right, now what's the next thing we want to do? Part B says to find local max and min. And actually we've already done that because looking back at my chart here, we said that the derivative is increasing from negative infinity to 4 and it's decreasing from 4 to 6. So that means if I'm going up and then down, that means that spot in the middle where I had a horizontal tangent line at 4 has to be a max. And that would be at x equals 4. And then if you want to write it at a point, and that maximum is f of 4, which is going to be 4 to the square root of 2. Okay, and you could write that as a point if you want 4 root 2. That's your max. There is no min, right? Because once we start decreasing, well, we just hit the end point of our domain. All right, so what's the next thing we need to do? So now they're asking us to find intervals of concavity and the inflection points. Now, those come from the second derivative. So I need to calculate my second derivative. And remember, my first derivative was right here. So I need to take the derivative of that, which doesn't look good because we might as well just use quotient rule here. And remember, quotient rule says low, which is down here, and high. We need those two elements, okay? So quotient rule says low, d high, the derivative of the numerator is just negative 3, minus high, d low, which is 2, 1/2, 6 minus x to the negative 1/2 power, times the derivative of what's inside of that, which is a negative 1, all over low squared. All right, so to identify our parts here, we had low d high, high d low, and here we have low squared. That's where we get all these parts. Okay, now we definitely want to clean that up a little bit. So how do we do that? Well, first let's deal with the coefficients. So I have a negative 6 square root of 6 minus x minus, well, let's see what happens. The 2 and the 1/2 cancel out. I have a negative out front, so actually make this a plus. 12 minus 3x times 6 minus x to the negative 1/2 power. We don't like that at all. In the denominator, we have a 4 times the square root of 6 minus x squared, which I know is 6 minus x, but just trust me for a second here. We're going to write that as 2 over 2, and I'll tell you why. We don't like that negative exponent in my numerator, so I'm going to get rid of it, and here's how I'm going to do that. I'm going to multiply this by 6 minus x to the 1/2 power. If I do that to the numerator, I need to do it to the denominator as well. I end up with negative 6 times square root of 6 minus x times the square root of 6 minus x just becomes 6 minus x. And then when I multiply it times 12 minus 3x times 6 minus x to the negative 1/2 power, well, notice when I multiply that by 6 minus x to the 1/2 power, I get 6 minus x to the 0th power. Right, it'd end up being this, 6 minus x to the 0th power, which is just 1. So we don't even need to write that down. And in the denominator, I end up with a 4 times 6 minus x to the, I got to add the exponent, so I end up with a 3/2 power. And that's why I wrote it as 2/2, just to make that easier on us. And so I can finally bring that together once I do all my arithmetic, and I end up with 3x minus 24 over 4 times 6 minus x to the 3/2 power. Okay, so to find my inflection points, it's basically like finding my critical points from the previous section by setting the numerator of my derivative equal to 0, and that will give me x equals 8, and then the denominator of my second derivative equal to 0. That's where my second derivative is undefined, and we get x equals 6, but we kind of knew that was going to be a problem anyway. And this is actually unusual, right? Because remember, my domain was negative infinity to 6, and I have an inflection point at 8, so that's not even possible. All right, so here I actually have no inflection points. Does that mean my concavity is undefined? Not at all. We can still determine concavity by setting a number line, all right? And we have no inflection point. We're ending at 6 here. We can just pick anything we want and plug it in to the second derivative. So for example, how about 0? Let's plug in 0 into the second derivative, and all we need to do is see if we get positive or negative. So I'm going to plug in 0. I get 0 minus 24, that's negative, and I get 4 times 6 minus 0 3/2 power, that's positive. So negative over positive. My second derivative will always be negative. Okay, so that tells me then that the concavity is concave down from anywhere on the domain. So that's negative infinity up to 6. Okay, we're concave down. All right, now let's see if we can pull all this together and draw a picture. And let's just recall again, concave down from negative infinity to 6. We have no inflection points. We have a local max at 4, and the y value is 4 root 2. We're increasing from 0 to 4, decreasing from 4 to 6, and our domain goes from negative infinity to 6. Okay, so let's see if we can get a good picture of this. All right, so here's 6. We know that that's kind of our boundary. We know we hit 0, 0. Here's the value 4, and I know that that's my high point. So here at 4 root 2, that's how high up I get, and I have a horizontal tangent line there. I know that we said that we are increasing from negative infinity to 4. We're decreasing from 4 to 6. And I know my concavity is always down, so it's going to be something like this. So if we're careful, I think we can figure out that we're concave down, staying like that, and then hit our max right at 4, and then go down to x equals 6. And so our graph looks something like this. So I think that's it. I think f of x looks like that based on the information that we put together. Okay, I hope this makes sense. You know, honestly, we were just calculating the derivative, solving for 0, making the derivative undefined, and then doing the same thing with the second derivative to figure out the concavity and, you know, our intervals of increase and decrease. The algebra can be kind of tricky, so hopefully that helped clear this up in this video. If you have any questions on this, I'd be glad to help you. Thank you for watching.